Good old technology here.
But for this, I just wrote like week 3 lecture all of that.
Lecture.
Lecture.
Yeah, just lecture.
It's like, all right, I'll write about friends. Like the tours of research.
Bio.
Let's not get most of
Yeah,
the ground.
printout.
It's types were like,
Yeah.
I did California. It was the only other one that you could think of.
Oh, yeah, I did find this.
Anyway, yeah, I think everyone.
I just need the USGS.
So Simon Fraser, just hold on a couple of minutes. We're trying to establish communication with Miguel and UFT.
Try.
Excited that.
Need a sign and put it in front of the camera.
Well, I just texted.
I didn't know exactly what he wanted, so I was typing out my own words.
Yeah, same.
And I just referenced the main page. Yeah,
Oh, okay, that would make sense.
Hello?
because there's like a bunch of other tabs you can go to.
Oh, take me back. Yes, we were talking about, but everybody was.
Actually, no, I have not. I need to get that.
We couldn't hear them.
Okay, Christy, can you, if you hear us, just thumbs up, please.
Trying to do it in Excel.
Can you talk at your end? Because we're not sure we hear you.
Hey, Laurent, it's not.
Oh.
Works now.
Okay, perfect. It works.
It's very quiet. There's just very quiet. It clips out.
Okay. So by the looks of it, U of T is stuck in a snowstorm or off camera.
There's no students here yet at U of T.
Well,
Okay, well, we'll get going. The lecture is recording or will be recorded, so the U of T students can join in, I guess, when they can. This is where I unplug everything.
Where's
Okay, so Miguel, Christy, you can start recording, and I will get going right away with the third lecture on shear zones. So welcome everyone. I gather everyone had success with the quiz last week. That went out pretty easily. The lab is still ongoing for some or for all. If you have any questions, concerns, please let us know. And we'll try to help out as much as possible. So today we, in a way, start a second module, but it's in fact a continuity on shear zones. But contrary to the first module, where I focused a lot more on qualitative assessment of shear zones and microtectonics and microstructural fabric elements, what I want to do with this week's lecture is bring you into the more quantitative analysis of shear zone. And for this, we will talk at great length about rotation in shear zones and focusing on what rotates in shear zones, how things actually do rotate depending on the type of shear zone. If we're dealing with a dominantly simple shear or a dominantly pure shear high strain zone, things will rotate differently. Things will rotate at different rates. And even we'll have a discussion also on variables. For example, aspect ratios of rigid objects that will rotate at different rates depending on their orientations and depending on their aspect ratios. Short stubby objects versus long objects will rotate at different speeds and even in some conditions rotate in different senses as well. So it'll be a little bit frightening when we're talking about rotation sense in shear zones and come to the realization that certain features can back rotate against the sense of rotation of a typical shear zone. So don't hit the big panic button as of yet. Hopefully this will make sense. And yeah, no, I saw you. Yeah. Hand away from that big red button. Okay, and we'll start slowly and work our way from essentially the definition of the end members of shear zones. Then we'll focus on two very important elements in describing and quantifying shear zones, looking at stretching rate and angular velocity. And when I talk about stretching rate, I will use this symbol here for stretching rate, and angular velocity, we will use W as the term describing angular velocity, or see it as rotation rate, the speed at which things are rotating. Okay? And then eventually we will move towards a numerical description of rotation and introduce the terms vorticity and spin, which are two different elements describing rotation as a function of the reference frame that we're dealing with. And don't worry, I'll introduce all these concepts in due time. This will be the first half, or the first hour, or the first 50 minutes. We'll take a break, and then we'll move to the second theme right here, and describe the rotation in terms of flow type, aspect ratio, and orientation. And again, this will be very numerical, as in a little bit graphical and mathematical. Don't worry, I'm not going to go on the deep end of math, but we'll talk about it from a numerical perspective. And finally, of course, I will bring you back to the real world towards the end of the second hour, talking about at least one geological example of how we can apply this to the analysis of shear zones. Finally, the third hour, after another break, I'll introduce the lab, or the second lab, which is Kinematics of rock flow in a crustal scale shear zone. And this I'll present as a tutorial, mainly focusing on how to quantify vorticity and use what's called the ridge and grain net, which is a technique that you will use in this week's lab. The OnQ site, the lab has been posted since last Friday. It's a zip folder that contains numerous files that you'll have to download. One of which is the actual lab assignment. There's a couple of Excel spreadsheet files, a couple of TIFF files, which are sizable, but to maintain the high resolution, I've kept them in TIFF format, so download these. And then also a couple of extra papers that you will need for Lab 2. And we will talk about that in the tutorial this week. All right, so first off, before I get into the theoretical background of rotation, I guess it's important to start just thinking about the why. Why should we care about rotation when thinking about shear zones? And I've just put a couple of images here from my collection just to show you that there's ample evidence, whenever we're looking at a ductile shear zone, of rotation. Objects such as porphyroclasts rotate. We have this example here, and my students here at Queen's are familiar with this example here. This is the example I describe as the bride with the veil tumbling down the stairs coming out of the church. There's the veil right there of the poor bride, and of course she's tumbling in a counterclockwise fashion, and the veil is getting wrapped around her as she's tumbling down, after having said yes, of course. The point here is that all these objects that you're seeing, and even this inclusion trail in the garnet, are testament to rotation. Even CS fabrics, and we've talked about that in the first week, the CS fabric that you're seeing in this diagram here is an indication that lines, not just objects, but lines such as foliations, flattening surfaces with progressive shear rotate in a certain sense. So we can look at all these features from a qualitative perspective and assess whether or not they rotate clockwise or counterclockwise. That is certainly a first step, but we can take a second step in quantifying the degree of rotation and the magnitude of rotation, or the intensity of it. Another reason why this is important, so whenever we're dealing with a shear zone, this rotation component is directly linked to displacement. And when we're talking about a displacement in shear zones, in a ductile shear zone, the key value here is gamma, shear strain, which is a function of the offset of the shear zone and the width of the shear zone. And that, again, we described and touched on this in the first week. And why is it important? Well, if you're doing any kind of gold exploration in the semi-ductile shear zones, for example, a good understanding of the shear strain value of those shear zones is giving you some clues at the amount of offset, and especially if you're looking for sheared mineralized bodies, having the amount of offset can be quite useful from an exploration perspective. So this is not trivial. All right, so back on the recap here, when I talk about the end members for flow in a shear zone, we have here on this diagram our undeformed square circle that can deform into two end member systems. Either we're producing here, in this example right there, a simple shear strain. And notice here that the thickness, right, or the distance between the two boundaries here in simple shear does not change with time. Okay, so the shear zone boundary stay at the same thickness during shearing in simple shear system. In the pure shear dominated system, which is this scenario right here, the boundaries of the high strain zone are getting closer and closer together with progressive strain. So the high strain zone is getting thinner and thinner with time. And finally, the general shear example, and let's face it, this is probably the system that's more common in nature than we want to think about. This is a sort of a in between the pure shear and simple shear, where we do have a offset component, the simple shear component, but also assisted with a component of flattening across the shear boundaries, such as the shear boundaries are getting narrower and narrower with time. So when we talk about flow here, as opposed to brittle style deformation, flow is an intrinsic character of ductile deformation. We will want to describe the instantaneous displacement of particles in the flowing rock mass. And that's the key. Now, what you have here on these two diagrams are a series of lines representing velocity fields. So imagine in the first case here, we have all these particles. I'm just going to put little dots here, little blue dots in this mass. At an increment of time, with pure shear deformation, each particle will change place, will move. And if we were to describe this here, so this one here will have an arrow, this particle here will move this way, these particles will move this way, these particles move this way. Okay? Maybe I should change colors here. So in pure shear, all the particles, and as we'll see later on, the lines will tend to move and rotate towards a flow plane, okay? Which we will call the fabric attractor. This is the plane towards which particles will try to flow towards to, and the lines rotate towards parallelism with this fabric attractor. In pure shear, we'll have this kind of velocity field pattern. In simple shear, things are very different when you look at the velocity field of particle motion. So here we have a system, a dextral shear system. and the particle velocity field will look something like this. Okay? To accommodate the simple shear nature of the zone. And of course, the fabric attractor in this case is also horizontal, okay, parallel to the flow plane or the dominant shear zone boundary or foliation in our shear zone system. Okay. So the particle paths are very, very different. That's what I'm trying to get to. Now, in any kind of system, whether pure shear, simple shear, or even the intermediate step, we can imagine the system as a series of arbitrarily oriented lines that will either rotate or not, stretch or not, depending on their orientation. In pure shear, if we look at lines with zero rotation rate, so lines that do not rotate through progressive deformation, in pure shear, okay, we have two lines that will never rotate. Okay, these are the two lines that coincide with the minimum and maximum shortening direction. In simple shear, there's only one orientation in the system that will never rotate. And this is this red line right there, this line that lies parallel to the shear zone boundary. In terms of lines now that do not stretch or shorten, lines that have zero change in line length through time, okay, in both systems there are two of these lines, but their orientations are very, very different. So, for example, in pure shear, these two lines, which are yellow right here, will rotate in opposite directions through progressive deformation. Okay, this line right here will rotate counterclockwise, and this line here will rotate clockwise through progressive deformation. In simple shear, these two lines that do not change length, one of these two lines is parallel to the line of zero rotation. The other line, okay, that defines the strain quadrant boundary will rotate towards the line of zero rotation with progressive deformation. Okay. Now, if we look at a series of strain ellipses from the finite deformation pattern on the left and the instantaneous strain ellipse on the right here. Okay, when we want to describe the finite deformation, that is the deformation you're seeing in the rock. What you're really looking at is the difference in distribution of particles between the initial and the deformed state. And for this, we'll need to have a good understanding of the instantaneous strain ellipse and looking at how the finite strain ellipse, which is XF in this series of sketches, how the finite strain axes change in orientation with respect to the instantaneous. We all know that in pure shear, that finite strain axes do not rotate with time compared to the instantaneous one. There is a rotation of the strain axes in simple shear, however. So let's have a look at the pure shear system right here. Okay, so what I've drawn here in orange, okay, are the lines of zero change in length, okay, zero stretching rate. These lines, okay, in gray right here are the instantaneous zero change in line length, and in orange are the finite ones. Okay, you'll notice that the finite lines of zero stretch rotate away from the instantaneous lines of zero stretch, and one will rotate clockwise, the other one counterclockwise. Okay. Now, if we look at the simple shear system here, a couple of things to keep in mind. There are two lines, in fact, if you think of it in 3D, with zero rotation rate. We already talked about the line that's parallel to the shear zone boundary, in this case the horizontal line. That's a line of zero rotation. There's another one that's oriented how?
Into the page?
Into the page, absolutely. Okay, so the third dimension here is key. There is a second line that has zero rotation, and that's the line that goes right into the board right here, perpendicular. Okay. In perfect simple shear, the instantaneous maximum stretching direction makes a 45-degree angle with respect to the shear zone boundary. Okay? And this is this line right here, xi. And in progressive simple shear, the finite strain axes will rotate towards the fabric attractor away from the instantaneous strain axis. And finally, the key component here, or the key take-home here, is right here. All markers, material lines, will rotate with the same sense as the imposed shear. In perfect simple shear, in this case here, everything will rotate clockwise except the two lines with zero rotation rate. Now finally, as I said earlier, the intermediate stage here is what we call general non-coaxial flow. That has simple shear and pure shear operating simultaneously. And in this case here, we have contemporaneous shortening across the shear zone. And this is the key component here. The shortening is then accommodated by extension along the foliation surface, along the shear zone orientation. So we have shortening that's operating perpendicular to the shear zone boundary. And in this case here, we have a fabric attractor, let's say that's oriented like this. We have an element of stretch parallel to the shear zone. And when I talk about the geological consequences of this later on, we'll see that it's very, very important for extrusion of rocks. Okay, we'll talk about that later on. Okay, before we get into the nitty-gritty numerical description, let's have a brief discussion on the frame of reference here. Because when we'll measure degrees, we want to be very, very clear what are we measuring in terms of angle. What is our original reference frame that we're going to use to measure angles? And there's all sorts of reference frames. You can pick your own, you can create your own, as long as you're systematic in using it, that's fine. There are two general ones that people tend to utilize. There's an external reference frame and an internal reference frame. Now, let's take the example of a perfect simple shear scenario where you have horizontal dextral shear along this surface right here. Okay? As we said earlier, the instantaneous stretching direction in simple shear will make 45 degrees with respect to that. Okay? So we could define right away what's called an external reference frame, which would be the shear zone boundary and its normal. Okay? And any degrees reported from there on are, let's say, alpha degrees clockwise measured from the normal to the shear zone boundary, or negative degrees counterclockwise measured from the normal to the shear zone boundary. That would be what's called an external reference frame. Or we could measure degrees with respect to an internal reference frame, and in this case here, the internal reference frame is our instantaneous strain ellipse. Degrees measured away from, let's say, the direction of maximum instantaneous stretch, clockwise or counterclockwise. Okay, I'm going to draw something now. that might be a little bit scary. Okay? So let's just assume that we have a shear zone that's oriented like this. Okay? It's a dextral shear zone. And then our reference frame is oriented like this. This is the normal to the shear zone boundary, and that's the shear zone boundary. Okay? And let's just assume that this is a perfect simple shear system. Okay, so we will draw the instantaneous stretch direction, which will lie at 45 degrees, and that's my instantaneous strain ellipse and instantaneous strain axes, ISA. So that's all fine. Any rotation sense, let's say documented within the shear zone here, will have, let's say, because this is simple shear, everything rotates clockwise. Okay? Now, let me draw you the bigger picture of what the system could represent. The limb of a fold. Okay? A fold that is deforming and forming by flexural slip. Okay? Bed on bed slip to accommodate the folding. Okay? So what is happening through time? This limb here is shearing in a dextral sense. Fine. But what did the limb do prior to folding? Let me use a different color here. Let's use black. The pre-folding stage could have been a limb that's oriented like this. Okay? So the limb itself rotated counterclockwise. Okay? In other words, the reference frame has rotated counterclockwise, but any object within the reference frame of our shear system has rotated clockwise. Does that make sense? Right. So, this is to introduce two terms now. When we talk about rotation of things happening within the shear system, okay, this is what we call vorticity. Okay? When the reference frame itself is rotating, we will talk about this rotation as spin. Okay? So let's just keep that really, really clear. From now on, we'll mainly focus on vorticity. Things that rotate inside the shear zone as opposed to the shear zone system itself rotating through time. We could have a shear system where the spin is clockwise and the shear zone is clockwise as well. Or we could have the opposite. Sort of different things. Okay. So now what we'll want to do is to describe the flow numerically inside the shear zone. Okay, so the first thing that we'll start with is, let's say, a progressive deformation path right here in A, where we have the square being progressively deformed in a simple shear manner. Okay, so all of these different squares represent a snapshot through time. Then let's take one time, and in this particular example here, we've stopped the clock at 10:33 precisely. And that's the snapshot of that deformation increment. Okay? And imagine in this volume or surface area all these different particles. And these particles are all moving in a certain direction at a certain velocity at that increment of time. And then in C here, we take these same particles, okay? Don't think about the particle path motion at this point. Instead, we randomly link all these particles such that we produce immaterial lines of all possible orientation in our surface. Okay, follow me so far? Don't worry.
Okay.
Things will get clear in a minute. Okay? Now, let's isolate one of these lines. Let's say this line right there. Okay? Which is this line in D. And for each of these lines, the key component here to describe the flow numerically is you need to describe for that given line how much is that line, or at what rate is that line changing length? The stretching rate. And at what velocity is it changing orientation? So those are the two elements to describe flow, the stretching rate and the angular velocity. And of course, we'll want to do this for all the lines to accurately portray all the possible orientations. How are we going to do this? And you'll be surprised how simple it is. So what we will do, and right after this, I'll get you started, and I'll want you guys to actually do it yourselves, okay? And maybe join up per table and come up with a numerical description of a particular example. What you'll want to do is produce two diagrams simultaneously, two plots, one of stretching rate, plus or minus, versus orientation, and another plot which will have the angular velocity, W, over orientation of line on the x-axis. And we will produce two curves that will portray the variation in stretching rate and angular velocity for all possible orientations between 0 and 360 degrees. The shape of those two curves will give us a direct quantitative assessment if we're dealing with pure shear, simple shear, or 20% simple shear, 70% simple shear, and so forth. Okay? Okay, so let's go back to our board here. Okay. Everyone take a pencil or sketch something. We will first define, and we will talk about, in this scenario here, pure shear. Okay. And we will produce these two plots. Okay, so I'm just going to draw here. This one here will be the stretching rate, and this one here will be the rotation rate. And on the, so this is plus, minus, plus, minus. Let's arbitrarily set the plus as being clockwise rotation, and then the minus counterclockwise rotation. And on the x-axis, we'll have degrees, so let's just put this here as 180, 90, 270, 360. We'll do the same thing for this one here, 180, 90, 270, 360. Notice that the two plots are stacked on top of each other, okay, so that the 180 coincides with the 180 down below as well. So let's define now our reference frame, because it's key here in accurately portraying the angles. So we're dealing with pure shear, and in this case here, we're doing something like this. There's our instantaneous strain axes. Okay. And this is our reference frame. Okay, so we'll have, that's representing 0 degrees, this is 90, this is 180, this is 270 degrees. Okay? What orientation is the fabric attractor in this particular scenario? It's oriented at 90 degrees, 270 degrees. Okay, so that will be our fabric attractor in pure shear. Okay. So let's just now imagine a whole series of lines. Okay, of different orientation. Okay. Now, we'll start very simply. Okay. We'll start with a line that has 0 degrees orientation. And that's a line that's oriented like this. Okay? Vertical. Now, let's start with the simplest. In pure shear, is this line rotating or not? It's not rotating. So what is the rotation rate of that line?
0.
A big 0. Let's put it on the plot right here. It's right there. Okay. What about stretch? What is this line doing with time?
It's getting shorter and fatter.
It's getting shorter. By how much? A little bit? A lot? It's the maximum. Okay? So let's just, I didn't put any values here, but let's just put it down here. Whoops. Okay? So that is this line right there. Okay? Now, let's look at a line that's oriented parallel to the flow plane. Okay? And do the same thing. Okay? What is the rotation rate of that line in pure shear?
It would be 0 as well, because it's not moving.
Absolutely. It's 0 because it's also parallel to the fabric attractor. Okay? So it's oriented right there. Okay? In terms of stretch, what is it doing?
Nothing.
Nothing?
Stretching.
It's the maximum amount of stretch. Okay, at 90 degrees, oops, is right there. Okay? So, now let's think about all the lines between 0 and 90 in terms of stretch. What are they doing? you will have a field where all the lines will be still shortening up to a point where you get to an orientation that marks the line of 0 change in length, okay, which will be right there, okay? And then you'll go towards lines that eventually stretch. So lines that will shorten, and then you reach the positive value, lines that will stretch.
Will that be sinusoidal, or would that just be linear?
Hold on.
Okay.
Okay, we'll get to that in a second. Okay. In terms of rotation now, all these lines, okay, all these lines here in this quadrant between 0 and 90 rotate clockwise or counterclockwise? They all rotate clockwise. Okay? The rate at which they will rotate, okay, will look something like this. The line that will rotate the fastest will be at 45 degrees. And then by the time it reaches 46 degrees, it's slowing down. Okay? So what I want you to do now, okay, is complete this diagram all the way to 360 degrees. Okay? Giving you 5 minutes per table. Okay? Do the same thing elsewhere. So complete this diagram for 90 degrees all the way to 360 degrees. Okay? Work as a group. I don't care. Try to finish this class.
What's 90 equals 45? Yeah. It like actually works.
And?
Like this one definitely.
Yeah.
Triple the cable here. Okay. Now find your instantaneous stretching axes on those sinusoidal curves.
Tangent. What was it? That's instantaneous. Yeah.
Just,
You said find the instantaneous stretching axes, and it's just any tangent.
Who would have thought?
They're offset.
Would never have guessed that.
This is like,
No, because there's only one for any given spot.
Okay. If you're done, find the instantaneous strain axes on those two curves.
No, he just said like what is the
really, because every conversation he has, he's like, are
So
you
for
sure you're
those
gonna
of you
have
done, okay, on your two curves, find the instantaneous strain axes.
Like that sense you get whenever you talk to them, you feel completely happy, right? So I'm getting that. Oh my God. I like shrieked in my room to the point where a resident knocked on my door because it's like, I wasn't that bothered,
Where your
but now I know.
T is 0. Or W is 0. Because that's your component of rotation. No, why? 90. That means that's
Because that's happened to them before.
He said find
your axis.
like
Your ISH is like 91, 180.
Sorry.
It's where, yeah,
Right.
it's wherever W is equals 0.
one W is 3.
Actually,
Oh, it's W to me.
Alright.
It's W to me, man.
What is it actually?
It's omega. It's a little omega.
Just a cute little omega. Just a cute little omega.
45.
My hand.
Really weird. Just like, fill them out.
No. Can you be actively working on this lab project? Before what?
That's the setting of like a weird. Yeah. I don't think any of them work.
Everyone done?
Yeah.
More or less?
Where is it? I want to say that's like the civil building.
Okay, so you'll notice that when we've done that, okay, you've actually produced a numerical description of all the lines of all possible orientations and described their change in stretch values and change in orientation as a function of their general orientation on our framework. Okay? Do the same thing for simple shear now. And then we'll talk.
Not sure it's the same.
Okay? So if you're doing it in simple shear, come back to this later. Do the same thing.
We're doing dextral.
And let's do dextral. The idea is to keep it systematic.
Or like that's like something.
These are now at 45 degrees, right?
Yep.
The ones near the middle are shorter. Oh no, those are just,
Oh, I did.
because like this line, for example, would be rotating a lot. Like counter.
Yeah, so it's
And if we do like just 0, 180, it's rotating the most it could be clockwise. It's always rotating clockwise. So it's just.
I didn't really understand what you said, but the instantaneous.
Oh, the one.
So, okay, the instantaneous strain axis, there's a horizontal one and a vertical one, right? Where's the
0, like omega is 0, and W is 0.
the maximum?
Yeah.
That one there, right? Which coincides with zero. Okay?
There's only one line.
And this line here,
Yeah, 364. Oh, sorry, I mean 279. Pardon me.
so that and that, the angular difference in these two is definitely.
Because I think there is one line, but like it has the origin again, you know.
And this line here,
And then at
that has
90,
a minimum stretch.
oriented, sorry, if it's oriented to 180, it has maximum again.
I don't know why I went negative.
And if it has, it's at 0 or 360 again.
It'll look very funny.
Yes,
You
kind of
locate, so
clockwise.
these ones, circle that as a
think it
color.
should.
These are the two same lines. Okay?
And are any of them stretching? Oh, I did.
He just wanted us
Oh, yeah.
Okay, and when you're done, just like I did in the previous one, find and locate your instantaneous strain axes. So if I go back to this example here, okay, the lines of maximum and minimum stretch, this line there and this line here, okay, are separated by 90 degrees which kind of makes sense because the instantaneous strain axes have to be at 90 degrees to each other by definition. Okay. And in pure shear, the line of maximum stretch is a line with zero rotation. And the line with minimum stretch is a line with zero rotation as well. Okay? So these lines here and these lines here are your instantaneous strain axes in pure shear. Okay? So do the same thing in simple shear.
Oh,
Got it?
yeah.
More or less? Go here. So you should have something that looks something like this. Okay?
Bounces.
Okay?
Yeah. Because it only rotates.
And your instantaneous strain axes in simple shear now, yes, they are the two lines of maximum and minimum stretch on the sinusoidal curve in the first diagram, but the bottom diagram has lines all on the plus side, rotating clockwise, except every 180 degrees on the foliation plane where rotation rate becomes zero. Okay? And there is an angular difference between the instantaneous strain axes, the lines of maximum and minimum stretch, and the lines of zero rotation rate. They're at 45 degrees to one another. Okay? Numerically, that's the fundamental difference between pure shear and simple shear. Okay? So I'll just finish very quickly on a couple of diagrams that you guys already have in your handout. Okay? Here in this slide here, the reference frame is just tilted on its side at 45 degrees. Don't worry about it. What's important here is not the fact that the fabric attractor is oriented like this and our zero is horizontal. What's important are these two diagrams right there. Okay? You'll notice that in pure shear, okay, especially when we talk about this diagram here, we have an equal number of lines that rotate clockwise to a number of lines that rotate counterclockwise. If you add all of these rotations together, you'll end up with a rotation, a bulk rotation of zero. Every clockwise line is counteracted by a counterclockwise rotating line. So pure shear is why we call this a system with no bulk rotation. It does not mean there's no rotation, but the sum of the system has zero rotation. Okay? We call this a system with zero vorticity. We'll get to that right after break. In simple shear, this line here has moved up completely so that all the lines rotate in one sense except the lines parallel to the fabric attractor. You add all of these rotations, okay, you'll end up with a single rotation sense, okay, vorticity equal 1. General non-coaxial is in between, okay? The diagram here will look something like this. Here we have most of the lines rotate clockwise and some a little bit counterclockwise. Here's a catch-22. This would be a dominantly dextral simple shear with a little bit of pure shear because we have lines rotating counterclockwise. So that means we have lines, objects in this system. Although the entire shear zone is simple shear dextral, we have lines rotating counterclockwise. Okay? As soon as we add a pure shear component to our shear zone. And unfortunately, ladies and gentlemen, that's nature. That means you may be looking at a myelinite, a shear zone in thin section, and you'll have objects rotating the opposite sense to the shear zone that you're documenting in the field. Okay? Welcome to real world. But what we want to quantify now, and you're going to do this in this week's lab, is find a way to calculate that, to quantify that deviation from pure shear, and come up with a number that you can, and by measuring features in the thin section per se, and there are techniques for that. Okay? So the last thing I want to show, and then we'll take a well-deserved break here, okay, is if we talk about vorticity, okay, we're talking about how, at what rate lines are rotating, okay? What happens if we're doing an experiment here at Queen's and we use a 1960s rig that's shearing very, very slowly, and then of course the McGill crowd comes up with the 2017, top of the line shear zone apparatus, and they can run the same experiment much quicker. And then we try to compare our results. What will happen? The rotation rates will be totally different, although we may be documenting the same shear zone. So we'll want to normalize our rotation rate to shear strain rates. And in doing so, this is where we come up with this value called the kinematic vorticity number, which is the sum of all the rotation rates normalized to the shear strain rate. There's another way of calculating WK, the kinematic vorticity number, and it's using this, cosine of beta. What is beta? Well, beta is the angle, the minimum distance between two lines of zero rotation rate. So, in pure shear, there are two lines that do not rotate, correct? Pure shear, they're oriented perpendicular to one another. Okay? What's the minimum angle between two lines of zero rotation rate in pure shear?
90.
90 degrees. Cos of 90 degrees?
0.
0.
0.
Okay? So that's the kinematic vorticity number of pure shear is WK equals 0. What is the minimum angle between two lines of zero rotation rate in simple shear?
45.
No, it's like 60.
Oh dear.
Is it 60?
In simple shear, there's only one line that never rotates. Okay?
Change, yeah.
So cosine of 0 equals 1. Okay? Simple shear, WK value is 1. Okay, now, what would be the WK value if you have a shear zone with 50% pure shear, 50% simple shear? Okay,
0.5.
so simple shear is 1, pure shear is 1. What is the WK value for a shear zone with equal number or content of pure shear and simple shear? 0.5? What is the
root 2 over 2?
cosine of 45 degrees?
Probably 1/2.
No, it's 1.
It's root 2 over 2, right?
0.72.
Yeah.
Okay? So here's a very simple diagram here. Percent simple shear versus the kinematic vorticity number. Percent pure shear 0, that's simple shear, we have a value of 1. we have a value of 0 in pure shear, and that's essentially a curve representing this equation right here. Every degree between 0 and 90 degrees. 50% pure shear equals to a WK value of 0.71 something. Okay? Let's take a break. Right? You guys are all stunned, so let's just break now. Before there's people passing in.
Relay this information.
All right, Miguel, Simon Fraser, we're good?
No.
Oh, Toronto is there.
Yeah, there's
No.
no Patrick. Can I work on next week's lab? Instead of doing band today?
It's fun.
Work on next lab.
No. Is it remotely? Is it incredibly stressful?
Oh boy. Man, I was so ready to be early today.
I
And I
don't
got
have a job.
like halfway here and I realized I forgot my entire bag with all
I mean, I do.
a laptop and my music and everything at home. So I was like,
When it comes to organization, or is it okay if I split them between the questions? This is for
Okay, so those are, no, they can be.
They can be bottom line here by my section. I just did that to you.
Oh, yeah, I'm down for that.
Didn't know if you wanted to like pair.
No, it's that.
But come in like,
No, it's fine if it's broken.
what about his name, Doctor?
Easier to see.
It's like a
Next, I appreciate that.
like I've written everything up. I just need to freaking annotate all these different
That needs to
pieces.
be
Otherwise.
Yeah. Yeah. I mean, I've got a system now, but
Yeah, I've heard that actually, yeah.
Yeah, alright, that's not too bad though.
Get your mobility.
So that's annotated.
Exactly, it's already flat.
Yeah, I think
So I think that's
Even
why,
water
because
running.
these-
It shows minerals and regime utilization.
Yeah, I just, it's,
What regime?
Because
let's
then
just
that's
describe
why-
that.
No, definitely not. Figure caption.
Put it in the figure caption. Okay, yeah, makes sense. Thanks.
Yeah. Your caption should highlight what you want to tell me.
You're okay with point form for like in the description part?
I haven't done it before, so like this one is.
Okay.
That one.
We should get Illustrator.
Illustrator is amazing.
It's like.
We should get Illustrator.
I've been, I
Yeah,
don't know what
totally.
I've been doing it on.
Yeah, here. Adobe Illustrator, it's the best.
Illustrator?
Yeah.
Just like kind of.
Yeah, so I set up a bunch of layers for me so I can turn like,
Or not?
if I need a different scale, I can turn that on, if I need to like,
Is,
Oh man,
Stuff like that.
I'm drawing
Yeah.
in Word.
yeah,
fun
no,
one
drawing
way,
word
because this
sucks.
is my other.
Does.
Is that like localized or?
Yeah, so and then I save this as a template essentially, so I can like save a copy of this,
That's why
and
this
then
one
got that, I can
I
just like
think Laurent
This one.
get rid of that photo,
go
upload a new one,
this.
put in
Okay.
my new whatever I need. Yeah,
That's
it's
beautiful. That's amazing.
so much easier.
Oh
Yeah.
man.
Adobe Illustrator. I mean, yeah.
Simple.
Like,
What's that
With a
cost?
tiny bit of pure shear though.
So yeah,
I just distorted it. I distorted it.
Maybe not
Correct.
for
Set my firewall and all that.
This would
But
happen.
normally several hundred.
If you have a lot of pure shear, it's
So, but I mean, I asked Laurent to pay for it because as like a research campaign, he's like, he tried, but NSERC was like, no, you can't buy Illustrator with
You
NSERC
would
money.
have like
He's like, okay, well, then I'm just gonna look the other way while you all download it.
one in the middle
So-
shines sinister.
Yeah, it depends on the,
Yeah.
And I've been slowly typing it in Word and just like drawing with my mouse.
Yeah, that's, I would go mad if I
PowerPoint's a little bit better than Word.
PowerPoint?
Yeah.
Well,
Just
Word
it lets you
has
do a
this-
little bit more.
Word had like a draw feature for a while, but then I reopened my computer and it just disappeared. I have no idea how or why.
really the take you get from that is that these all shear zones observe one single.
the structure indicator. Don't build a full interpretation that your shear says switch from one to the other. It might be backward. Sorry. I'm a very jittery person. Boo. Sorry. Your head was right here. Yes. We've gotten everyone's attention to class.
401.
Yes, I still need to go talk to Lark about that.
Okay.
I'm assuming I've effectively screwed myself over in some sense.
No, but
like,
no.
No.
I think that everything can be remedied.
Okay, that's
But
nice.
you
That's nice to
need
hear.
to initiate.
Gotcha. I can do that. Is there a time constraint on that? Because I was just planning on going in one big
I
bulk.
would say sooner rather than later. But probably start with
This.
Society or something.
That's what I got for it. I think
registrar
A1.
but you can
The
retroactively
other one.
drop
The
it.
big thing is
Yeah.
like it's
It's
like.
just, you essentially forgot to do it.
Yeah, like
Right.
literally. Was that?
Yeah, so, but I mean, both Nolan and I are fine with supporting you, so that, just erase it, right?
Okay.
Because you don't want that, right?
No. God, no.
Considering you're planning to
But like.
do it
Yeah.
this fall, right?
Sorry. Yeah, like next year.
Yeah, so let's just make sure
Where
that,
this overlaps, doesn't always show.
I don't end up with an F. Yeah.
just clean that up.
Do you not remember the cost from some? We only have one.
No, I didn't.
Oh, I have two.
I actually just did.
So you paid for it as well.
Yeah. I won't pay for it next year. I don't think you understand just like my level of
No, I think I very
disorder.
much
Okay.
do.
No, there's a whole like underbelly you haven't seen yet.
Okay.
But because it's but like you said, we finish this one. Isn't
I think on average there's a week of a semester where I'm well organized, like just 7 days, and then
medium.
not in a row even, just individually placed. Commitments like this, like I've been practicing for this test tomorrow for like a good 2 weeks, but
Or like do like 100 miles. Because it's not like.
yeah, well, we're singing with the KSO. You actually have to be like good, like as in like you can't just know notes like other shit.
Hold on, we've been on break. I don't even know. I don't know, man. It feels like I've been on break for like 20 minutes. Serious? Yeah, I don't know how long I've been on break. It's like we just stopped.
I don't know.
I honestly have no idea.
There's different ways of counting.
Yeah, like
We
this.
could count
Who's here?
who's here, we could count who's registered
Yeah, if I were awake, it would have been better.
Then there are students registered here but are doing it, but they're using an exchange program, they're registered with me. But because it's got the capacity, then we can look at it. So different answers.
Yeah, it just feels like a lot.
Unadulterated.
I think a lot of people
This is how I made my entire poster. I represented I went to a big structural geology conference in Muskoka. October? November or so? And yeah, I had to make a poster to present there, so I just essentially started an illustrator, like a blank sheet, and then just went down. Here's the one that's hanging up on the fifth floor outside. Yeah, that was just like starting an illustrator with just like a blank canvas and built it from there. Steep learning curve. Like it's not like it's not the easiest program to just like download and then be like working on the but yeah, like there's a fairly steep learning curve to it.
I've been using Lightroom for the
Like
same
one, but I
idea.
don't know how to like edit in.
Okay, where do I want to
I don't
go?
know how to imagine
It's supposed to, it should automatically publish it, which is like version.
Yeah.
So if you try that, but sometimes it's weird and doesn't.
Oh, you have that? I was like, why is it?
My name
I got like 4 things.
Because
I forgot.
I'd rather format it in actual.
Okay, how do you go to the grocery store and get less than you need? I always go there and end up having way too much stuff.
Yeah, Patrick.
Yeah, that's not
I told you I was going to the grocery store yesterday. So I went and was
Yeah.
like, what do I need? I was like, I don't know. So I only got eggs and I got bread and then I left. I was like, what do I need? And I was like, I don't know. I know I need eggs. I need bread. And I picked up orange juice to be like, oh, I think I need this. And I was like, no, I don't need this. And I got home and I have like no orange juice.
When I get into those situations, I end up buying
No,
that I like don't really need.
I like walked around the place like 3 times and was like, I don't know what I need, so I'm just gonna leave.
See, that's better. Mine is like, I don't know what I need. I guess I'll buy all these things. I guess I'll just buy everything. Exactly. Yeah, no, I get it.
But you don't realize what I eat mostly. I eat.
You had those weird little pizza pop.
Yeah, and then, you know, every other day I have ramen for dinner.
Oh yeah?
Yeah.
Every other day? I could not live that life. I live that life.
Yeah, well, you don't live the life of someone who's really late.
Yeah, that's right. I don't know, I just love cooking. Like, I just really love
When I'm cooking, I love it. But when I'm like, oh god, I gotta cook, I'm like, nah, yo, just throw me that wrong tonight.
Oh man.
It's creepy too.
Yeah, she knows it.
Unless you're like,
I have some that I like frozen. Oh, I have sausage sensation.
I'm telling you.
How about those?
I'm not. But the name sounds
It's like a frozen PlayStation, like just throw in the pan. Cooks, but it's like there's so much salt in it though.
That's just not great.
It's so good.
It's easy and it tastes good.
Yeah, it's easy and it tastes good and it looks like it's healthy. So that's enough for me.
Fair. You know what?
It's like chicken Alfredo. I'm like, oh, that's good. And then you like chicken
Alfredo.
So Christy, Miguel, is everyone there? Can we
I'm
start again?
not here to tell you how to live your life, but you know what? You do you, man.
Other than ramen.
Is it?
Look at this body. Doesn't it look amazing?
Yes, yes. Yeah, I got you.
Thank you.
Yeah, it's
Oh, plug this in. I did plug it in. It doesn't work.
really?
Yeah.
Oh, it's
Yeah,
good.
each thing is like a
Yeah.
separate.
Well, I mean, you could plug that one in that,
Oh no, it's
Daisy chain.
and then I'll plug this one into that one.
Okay.
That seems like the best idea.
For the sake of trying to finish on time, we'll get going. Everyone's here. The Spirit Queen. Simon Fraser, you're there. Miguel? Yeah.
Now we're here.
Okay, perfect.
Let's do the thing. Here we go.
All right, so what we've just done is essentially go through the details of the numerical description of flow and how to hopefully have some tools to quantify the double K value in shear zones. Okay, so the pure shear, simple shear, and the values in between. So now we have a measure. Right? If I tell you that you're dealing with a shear zone with a WK value of 0.71, then you should know at that point that you're dealing with a shear zone with an equal component of pure shear and simple shear. Of course, now the big question is how to measure that WK. How can we get towards measuring and looking at a thin section and then finishing off with a value WK for that particular sample or shear zone, and then finally, where am I going with this? Yeah, and finally come up with geological consequences of this as well. Okay? So, so we've just talked about the flow type, the influence of the flow type with respect to the WK value. Now, in terms of rotation, I want to talk about aspect ratio and initial orientation of whatever feature you're looking at inside the shear zone. And for this, I have to introduce this character here, Subir Ghosh, He's an Indian, or was an Indian geologist that produced some amazing work. Namely, he wrote the paper that I consider certainly in my top 10 of structural geology papers of all time, that was published in 1976 with Hans Ramberg. The paper was published in Technophysics. It's a beast of a paper, and I will not give it to you to read. It's over, I think, 75 or 76 pages or so, published pages, so that's not manuscript pages, which would be a lot more. Half of it is mathematical, the other half is experimental. And on the images right here, essentially a summary of those very elegant and simple experiments that he ran. So Gosh, what he did the mathematical treatment of this, and then went to Hans Ramberg's experimental lab, and then produced all these experiments with him, and then they wrote this paper together that is still cited heavily today. So, I mean, paper that lasted over 40 years, and is still recognized as the foundation for objects rotating in shear zones. Okay, so let me go through the experiment very simply. So what you're looking at right now is a shear box experiment using essentially silly putty. So the background gray right there is very weak material that will deform in a cohesive manner in the shear box. So silly putty. The black lines that you're seeing here are pen markers. So they're just lines drawn on the silly putty for marker as a reference. They are not different materials with a different rheological property. So they're just passive marker lines, orthogonal before the deformation. And then embedded in this is this rigid object, a piece of wood, okay? Rectangular with a very specific aspect ratio. Okay, in this case here, it's 2:1. So what I've added on this diagram here are orange lines, which are vertical in this case. These are lines parallel to the immaterial marker lines. And then the green line, which is the long axis of the rigid object. Okay? The start of the experiment is exactly like this at time 0. And the immaterial line is parallel to the long axis of the rigid object. This is at time 1 now. Okay? So there's been simple shear, perfect simple shear imposed on the system. Have a look at those two lines now. The immaterial orange line, I realize this is a little bit dark, but the orange line is oriented like this, and the green line is oriented like this. What do you see?
It seems that the squishy stuff is rotating faster than the rigid stuff.
Okay, so is it the squishy stuff that's rotating or the immaterial line that's rotating? So the material itself is just its matrix, right? This is all just silly putty. It's not necessarily rotating. What's rotating is the felt marker line. Okay? Now, this line here, has it rotated faster or slower than the long axis of the object?
Faster.
Faster, because it has rotated more degrees in that same amount of time. Okay. So things rotate, in this case, in the same sense, but not at the same rate. Let's go at time 2 now. Okay. There's still an angular difference in the amount of rotation between the orange lines and the green line. As things rotate even more so, let's go to time 3 now. What has happened now? the green line, which is the long axis of the rigid object, has caught up with the orange line. So during this progressive deformation, what can you say about the relative rate of rotation of the orange line with respect to the green line?
Faster.
It started faster, and then by this time, which line is rotating faster?
Green.
The green. Or the orange line is slowing down. Okay. So as lines rotate, they change rotation rate. Some lines relative to the others slow down, and some lines with relative to others accelerate the rotation rate. So this essentially summarizes the Gaussian-Ramberg experiment. And the premise is, depending on the initial orientation of what you're looking at, the feature that was in a specific orientation prior to shearing, and also depending on its aspect ratio, that will govern how much and how fast that object is rotating, or not, for that matter. Okay? Now for this, we will use another XY diagram, and again, don't hit the big red panic button. It's pretty simple here. There are two axes to this diagram. The x-axis, okay, is just orientation. And the reference frame is defined right here in the lower left quadrant, okay? So that a 90-degree orientation is a line that makes 90 degrees with respect to the normal to the shear zone. So if we're dealing with a simple shear system, 90 degrees to the normal is the flow plane itself. Okay, and there's the 90 degree right there. That would be the orientation of our fabric attractor. Okay? And then on this, as we're doing experimental, and we run these experiments with different aspect ratios, we'll deform different objects of different size. Aspect ratio R1 is a 1 by 1 cube or square. This would be a aspect ratio 2 to 1, and this would be a 6 to 1 aspect ratio. Okay. We'll have two fundamental assumptions in this system here. One, the rigid inclusions are rigid. There's absolutely no internal deformation of those objects during deformation. They just go through bulk rotation with no internal deformation. Two, the matrix is Newtonian viscous. Okay? Very weak. The other axis of the diagram, which is the y-axis, is rotation rate normalized to the shear strain rate. And again, this is just normalized so that we can compare one experiment to the other that may not have operated at the same speed of shearing. Okay? But we want to normalize the rotation rate here. And then we'll produce a series of curves for these three different aspect ratio objects. Okay? And we'll get something like this. Okay? P here marks what's called a passive marker. After a series of experiments, Gaussian-Ramberg observed that whether you put a rigid object of aspect ratio 6 or draw an immaterial line with a felt marker, they behave the same way. Okay, so an aspect ratio that becomes equal or greater than 6 will behave the same way as if it's just a felt marker reference line in our flowing matrix. Okay, so that's called a passive marker. And then we have here the curve for aspect ratio 2 and aspect ratio 1 right there. Okay. So let's have a quick look at simple shear. Perfect, ideal simple shear, a WK value of 1. Okay. And let's start with the simple aspect ratio of 1. That's the square. And we measure the rotation rate during progressive deformation. You notice that the curve here is straight, horizontal. Rotation rate stays constant. That square will rotate continuously through progressive strain in simple shear and will never stop rotating. Let's take the passive marker now. That vertical line, the felt marker line that we saw in the diagram here, would be oriented right here. As it rotates towards the shear plane, it slows down until it reaches the flow plane. 90 degrees to the normal. Once it reaches the flow plane, what is its rotation rate? 0. Does it keep rotating?
No.
Because the rotation rate then is 0. It has found a sink position. It's done. It's not going to rotate past the fabric attractor. If that same passive marker has an orientation of 90 plus 1 degree at the start of the shearing, what will be its rotation rate? Be a value, but very, very slow. Then it will start rotating, and as it rotates, it'll get faster and faster and faster until it reaches the normal to the shear zone boundary, and then it will start slowing down again. Okay? And it'll go all through that diagram again. The key component here is the passive marker here is always above the horizontal line here. It's always rotating in the same sense, but at a different rate. Yeah.
Can it ever cross that boundary, or does it always just like turn just in time?
Well, imagine my pencil here that the shear zone is horizontal, okay? It starts like this, okay? Rotates really fast, and then it slows down, slows down, slows down, and then it reaches the shear zone boundary. It has a rotation rate of 0. It does not rotate anymore. Now, let's do the experiment again with a line that's oriented like this, plus 1 degree. Tilting it a little bit, I'm exaggerating the angle. It will rotate, but very, very slow. Accelerate, 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 accelerate. Decelerate, decelerate.
Okay.
Then stops at 0, and then does not rotate anymore.
Hey, Laurent, can you stop sharing your content for a minute so we can see your pencil?
If I stop sharing content, the camera will stop. Hold on. Stop.
Hey.
Where's the camera?
There.
Now I'm in the dark. Can you see me now?
Yeah, we can see you. Thanks.
Okay. My pencil is white, which is not great. There. Okay.
That works.
That works? Do you see my pencil?
Yeah.
Yeah, looks great.
Okay, so I start with a shear zone that's horizontal. My pencil is vertical. That will have the fastest rotation rate. Here I'm dealing with a passive marker of aspect ratio of 6 or greater. As it rotates, I guess counterclockwise for you towards the shear zone, it'll slow down. By the time it reaches the fabric attractor, it has a rotation rate of 0. Does not rotate anymore. It's done. Okay? If we do the same experiment now with my pencil being at 90 degrees to the shear zone boundary plus 1 degree, it will be tilted a little bit like that. It will have a rotation rate, but a very slow one. And then as it rotates, it'll accelerate to reach a maximum rotation rate when it's normal, and then slow down again until it falls at 90 degrees or parallel to the fabric attractor and becomes 0 again. Okay? So this is for a passive marker aspect ratio greater than 6. Okay?
Okay, so stop me if you're going to come to this, but it seems like the shape, if you're approaching a really high aspect ratio, then you're basically approaching a line, no matter what the shape is. But at an aspect ratio of 1, a square is going to have much more frictional contact with the matrix if they're coupled than a sphere, for example. We're assuming perfect coupling all the way through?
Yes, I mean, this isn't perfect. There are series assumptions here, but this is perfect cohesive deformation, ductile, where there's perfect coupling and no gap or overlap between the matrix and the class itself.
Okay.
Okay? Now, in between these two cases, there would be, let's say, an aspect ratio of 2. Okay? That would be a rectangle, short stubby monazite, for example, or whatever. Will have its highest rotation rate when it's at 90 degrees to the shear zone boundary. It will slow down when it becomes parallel to the shear zone boundary, but will still have a rotation rate. And that object will rotate past the flow plane and then continue going around and spinning and rotating. Okay? So in this particular scenario right here, only objects that have an aspect ratio of 6 or greater will come to rest parallel to the fabric attractor in perfect simple shear. Okay? Objects that are very long will initially have a faster rotation rate than short stubby ones, and then as they rotate, they become slower, and then the short stubby ones rotate, relatively speaking, faster, which is exactly what we saw in the experiment a couple slides ago. Okay, so this is in simple shear. Okay. If we add a little bit of pure shear now, so we're somewhere between 0 and 1, now things start becoming a little bit more interesting. Here we have different curves. Okay. We have the aspect ratio of 1, which is rotating at a slightly lower rotation rate, but still constant rotation rate. It's always rotating in the same sense of overall vorticity of our system. Okay. The passive marker will accelerate and then decelerate until it reaches a sync position. Okay. But we'll see that in this area here, there's a new field, a field of back rotation, where certain objects of certain aspect ratio at a specific orientation at the start of the shearing will rotate opposite to all the other objects. That's because there's a pure shear component. Okay? And there's one object here in this particular scenario is an object with an aspect ratio of 1.28. Okay, that's just the example that's given. This one here will come to rest. This curve now, at this point here, the green line has a 0 rotation rate. That means it does not rotate anymore. And it stops rotating not at 90 degrees to the normal of the shear zone boundary. It'll be oblique to the shear zone foliation. And it will stop rotating oblique to that. Okay, so its sync position is at a counterintuitive orientation. Okay, so let's just humor me for a little bit. I'm just going to go through another quick slide here. As we increase the pure shear component, okay, and here we are heading towards a perfect pure shear system, you'll see that the counter rotation domain gets bigger and bigger. Simply, as we reach or we get towards pure shear, there will be an equal number of lines that will rotate clockwise and an equal number going counterclockwise. Okay? And the object that will eventually stop rotating as we get towards WK value of 0 will be an object of aspect ratio 1. Okay? We never reach, well, the ideal WK0, the one aspect ratio would be along the 0 axis. Okay? Meaning there's no rotation. Okay? So the field of back rotation widens with decreasing WK value. So where I want to take this is written right here, okay? Is depending on the system that will have a specific WK value, there will be one object with a critical aspect ratio that will come to a rest position. So take it differently, is if you were to measure a whole bunch of rigid objects in a myelinite with different aspect ratios and different orientations, you may find that there's one specific aspect ratio class that has a very systematic orientation, not parallel to the foliation. That will give you clues to the value of WK for that system. So I'm just going to summarize these diagrams because I think that might be a little bit easier. For any given flow type, WK0, 0.2, 0.5, 0.7, or 1, okay, the rotation rate of any object is a function of the aspect ratio and its initial orientation with respect to the fabric attractor. In simple shear, that is in WK equal 1, the passive marker, or very long aspect ratios of 6 or greater, they rotate faster when they're at a very high angle to the shear zone, and then will rotate and slow down their rotation rate until they sink and stop rotating when they're at 90 degrees to the normal of the shear zone boundary. So in a finite structure that you're looking at, let's say this picture here in the field, okay, the different shapes that you see, their different rotation senses that you're recording is a direct function of the aspect ratio. In this case, it would be the aspect ratio of this class, this boudinage pegmatite. And how much it has rotated and at what rate will depend greatly to the type of flow in the shear zone and also its original orientation before it started rotating. Let's give you a real geological example now. Okay. So here's a picture, a vertical cliff somewhere in the Himalaya, and what you're looking at is a shear zone. Let me just draw here, maybe in here. You have a foliation that's dipping like this, okay, which is the fabric attractor in our shear zone. Okay, so if there's foliation shallowly dipping to the east, let's say, okay, and we have a boudinage pegmatite that's oriented like this. Okay, now just on this very simple outcrop, you have objects of different aspect ratios here. Each individual boudin has a different aspect ratio, and there's even an immaterial line with an aspect ratio greater than 6 here, which is not necessarily a physical entity. What is this?
The entire stream.
The entire boudin trail. Okay? So the short, stubby individual boudins are rotating or have this kind of orientation. And the line connecting the center of all these individual boudins has this geometry right here. Okay? This line here is tracking more of the rotation than the short stubby ones. Okay? This line, in a way, you could interpret it as recording most of the finite rotation, whereas the short stubby ones are more representative of the instantaneous stretching direction. So here you have your homemade shear sense indicator or vorticity indicator. Finite stretching direction rotating away from instantaneous, counterclockwise, and that would represent a shear zone that has this sense of shear. Okay? Okay. Let me just move quickly here to how we will quantify this vorticity. Okay. So what we will do and what you will do in the lab, okay, is do some vorticity quantification. And for this, we'll use the theory behind Gaussian-Rambert to try to back calculate which object with very specific aspect ratio has found its sink position, and then back interpret the WK value for that system. So each element here, and this is the key sentence in this slide here, objects that are rotating in a very specific flow system between 0 and 1 for WK or WM value, okay, will rotate either clockwise or counterclockwise, and will eventually find a stable sink position that will be unique to its aspect ratio and to that shear zone kinematic vorticity number. So, don't be afraid of math. This is very, very simple. Okay. So, RC here refers to the critical aspect ratio that finds its sink position. Okay. So here we have a shear zone, a dextral shear zone, that has a component of pure shear. So it's a general non-coaxial shear zone with a component of flattening perpendicular to the shear zone boundary. So some objects will rotate clockwise, some objects will rotate counterclockwise. This, for example, here is an object with an aspect ratio of 2. Okay? Long axis, twice as long as the short axis, perpendicular to it. We can talk about aspect ratio or the critical shape factor, which is the B star. Again, don't hit the big red panic button. B star, the critical shape factor, is essentially the long axis minus the short axis square over the long and the short axis sum. Okay, so the MX and MN stand for long axis and short axis. So you can convert your aspect ratio of 2 into a B star value of 0.6. And it'll become obvious why we're doing this, because we're going to use a curve diagram. Okay? So here we have a diagram that shows the kinematic vorticity number between 0 and 1, and then the aspect ratio right here. And this curve here represents the stable sink position of a specific aspect ratio class for a given kinematic vorticity number. So there'll be a unique combination where we will match the WK value, the aspect ratio, and the angle of repose, the sink position of that specific class. We can measure this in the thin section. We can measure this in the thin section very easily. All you have to do is, let's say, look at this myelinite in rigid class, measure long axis, short axis, and then measure the angle between the long axis of this class and the fabric attractor. That's all you need to measure. Aspect ratio and angle. Then we will use and plot these results, and there's different ways of plotting this. I'll just show you very briefly the 3 different dominant plots, and then I'll go through in detail the one that you'll be using. This is called the Pêchier plot for Case Pêchier, who was one of the first ones to see value in this approach. What you have in this diagram, here is the angle, clockwise or counterclockwise angle between the long axis of these feldspars. And here is the B star value, which is essentially an aspect ratio or the critical shape factor. You see that short stubby objects that are oriented in this field or between -10 and -90 degrees, there's a huge range of orientations for these class. That means they're freely rotating. And then there's a cluster here and a sharp break where class of longer aspect ratios tend to have a more systematic orientation. The break between this field of free rotating and not rotating anymore, class, defines the limit that is a function of the WK value for our system. Here's another diagram. This is the Wallace plot. Again, it's the same thing. We have angle here with respect to our foliation, and here instead of using the B star value, it uses only the R value, aspect ratio. A huge range of degree of orientations for our class, and then in the right-hand side, we have class that have a much more limited range of orientation. And finally, the last one is I guess the Jessa plot or the rigid grain net, which is portrayed right here. And again, it has very similar angle between foliation and the class long axis. And then all these individual circles are measured, classed in our myelinite with the orientation of these long axes. And on this here, we have the B, which is the B star critical shape factor. All right, here's what's really important. Just like any technique, we have to be very wary of the assumptions and the conditions for which we can utilize this technique, okay? We need to be doing this in myelinites that have a high degree of strain to allow as much rotation as possible. There's not enough strain in these rocks. What we're seeing may be just an initial component of rotation, and the rigid class have not rotated into their sink position. We need to be able to measure a large quantity of rigid grain, but most importantly, grains that have no evidence of internal strain. If those class are not rigid but deform plastically and change aspect ratio during progressive deformation, this method is flawed. We need to be able to measure a large variety of aspect ratios, especially in the range of 1 to 3. If we only measure aspect ratios greater than 6, of course those aspect ratios will come to rest in the fabric attractor. Okay. We have to be careful of any dynamic recrystallization process affecting the rigid grains. The grains have to be pre or synkinematic, and this is a problem because in many shear zones we can have an influx of feldspars through injection of pegmatites during the shearing. So the shearing may be partly undergoing and suddenly we inject new freshly oriented grains that haven't been subjected to the bulk rotation. So that's a concern. We need a matrix that's homogeneous, and we need significant space between the class so that when they rotate, they don't interact with each other. Think of a series of logs in a flowing river, and you're trying to document the logs as they're rotating in the flowing current. If the logs touch each other, they might impede the rotation or create back eddies, and then there's back rotation of those logs and so forth. Okay, so you have to be careful with this. Okay. Why is this important? Okay, and I'll finish with this, and then we'll have a very somewhat short discussion in a tutorial about the rigid grain net itself and how to work it. Okay. I'm going to go back to an example I talked about in the first tutorial, and this is going back to my stomping ground in the Himalaya. And here we have a cross-section of the Himalayan system, India being on the right hand of the diagram, Tibet on the left side. Of course, the Himalayan system is a south-verging thrust system where all the thrust sense is directed to the south. And in the core of the mountain belt, we have this unit right here of high metamorphic grade rocks that have undergone significant ductile shearing. All the shear sense indicators in this package is dominantly top to the south. Importantly, the top boundary is a normal sense fault and the lower boundary is a reverse sense fault, and those two faults operated simultaneously. And there's been a long-standing debate on how this package of rock was extruded to the surface by coeval motion of those two faults. Either we have a dominant simple shear system, which is depicted here, where each and individual foliation plane acts like a card deck, and we have a dominant simple shear system here. Or we could have a little bit of pure shear pressing down on this system, closing the shear zone boundaries, getting them closer and closer, and then favoring extrusion of the material between those two boundaries. Okay? And of course that has direct consequence of how much stretching there is operating parallel to the foliation. And you can convert stretching here in extrusion. How much material is being extracted from down below along the foliation plane towards the surface. Okay? Each component, whether you're dealing with pure shear in discontinuous displacement mode or continuous displacement mode, will produce very different exhumation paths. So this is just a summary of an exercise that a whole bunch of people did, looking at the vorticity calculation using the Gaussian-Ramberg approach. Looking at thin sections such as this, looking at fine-grained myelinites and rigid clasts that ideally fall and follow the assumptions and the conditions that we set forth. And between you and me, there's no sample on the planet that has all those conditions satisfied. So if you take this with a grain of salt and assume that all of this has been respected, what's interesting, and here's the top boundary of the metamorphic core, here's the lower boundary of the metamorphic core. There, at least when this study was done, the boundaries have a greater component of simple shear, and the middle of the package has a lot more pure shear to it. So within this great package of extruding metamorphic rocks, just using this approach on several samples, measuring hundreds of clasts, we can document a progression of simple shear towards pure shear in an individual shear zone. Okay? Everything else looks the same. Every single foliation plane has a demonstrated top to the south sense of shear. It looks like a simple shear system, but by measuring the class, we can document that there's a significant component of pure shear in this system. Why is this important? Here's some scary math, but again, don't look at it. Look at this system right here. If you have a general non-coaxial system where you have simple shear and pure shear operating at the same time, as you're pressing down on this system like this, the material that's inside the shear zone needs to go somewhere. Okay? So with pure shear comes a high degree of extrusion, of stretching parallel to the foliation. From a geodynamic perspective, if you look at it from a Himalayan perspective, by having a very significant component of flattening, okay, you need to have this accommodated by foliation parallel stretching. And assuming plane strain condition, and this is where you use this kind of scary equation, which is really simple. R here is aspect ratio, and WM is the kinematic vorticity number. Okay? That's all you need. Then you get S, which is the value of stretch parallel to the foliation. Okay? And then you can convert that into foliation parallel stretching, or conversely, foliation perpendicular thinning. And you can actually quantify this. Okay? So all of this is done by using the kinematic vorticity number and the background of Gaussian-Ramberg's experiment. Okay? All right, any questions on this? Before we take another breathing break and then go through maybe 20 minutes at most of slides to talk to you about the rigid grain net that you're using this. Okay? Think about it. If you have questions, you can always email them to me later on, and then I reply to everyone with the answer, and then we can get going with the course. Okay, so let's take another 10 minutes, and then hang in there. We're going to be done with this, hopefully by 12:15 at the latest.
On the floor. So I'm looking for one.
I'm just thinking about all the structures I'm going to do after this.
Yeah, that's what I'm thinking now.
After what?
I need you to sit with me and just like wake me up.
Just like throw
Oh,
water.
I'm not even going home. I'm going back
So
to
bad.
Norway.
It's like, I was like,
You see.
Good plan.
I start like daydreaming.
Oh,
Like I hear it. Daydreaming.
are you going home or are you going back to Melbourne?
And my eyes closed.
I don't have anything I can do right now.
Yeah, I kind of have it all.
Oh,
Yeah.
I should work somewhere else. I've been in Miller too long the past 3 days.
Yeah, I'm not sure.
I don't know.
I need a different setting.
Carly and Magla and I got booked the
Yeah, no.
hotel back in my point.
Oh, nice.
you need
Yeah,
to jump
because
with
like
the-
last time I ended up just like going back from Hampton.
Almost just mostly sort of.
Yeah, that's the same. We're like almost sort of kind of close. Close,
You guys are close to it.
probably.
Like, I haven't finished my photos yet.
Geophysics scholarship.
Oh,
And
I
then
dropped the course.
like
Oh,
company.
good.
Oh no. Yeah, and she's been like invited to like a bunch of that like
I know, it's been a really good weekend.
like they
Yeah,
said
no, I
guys
bet.
My sister, she did.
foundation.
Okay.
I can just jump in
I
like
got
a
a
group
group
of
of
three.
yeah.
So
I
do you
don't even know if she's doing that. Like
Yeah,
she's
sure. I don't know. It's an excuse for me to go home and ski for a weekend. So.
true.
It's all about texture.
I just got a
Oh, mine's
email being flighted out by student council execs.
Yeah, you go 2 seconds. And then you click on battery.
I'm gonna go for a walk.
Yeah.
What do you have to do? What do you have to do?
It's RSVP.
Oh.
Laurent, are you talking right now? We can't hear you at SFU.
We can't hear you either.
What does it consist of?
Ah, good old mute button.
Has he started already?
Oh, no, let's start right now, if everyone's here and ready to go.
Excellent.
Go is ready.
Okay, so what I want to do here, and it's going to be pretty simple, I want to go through the vorticity plotting technique. So I very briefly went through the different diagrams that look very complex, but about vorticity and how to measure rigid grains in a myelinite. But I sort of want to debunk this and make this very simple, and you'll see you're going to be using an Excel a macro spreadsheet that's got everything built in, so you really won't need to do too much heavy-duty data handling. But you do need to know how to read the rigid grain net, and that's what I'm going to try to do in this tutorial here. So this I just talked about before the break. The idea here of quantifying vorticity is essentially trying to use rigid grains in your myelinite, measure their orientation and aspect ratio, and then back interpret the kinematic vorticity number for that particular sample. And the premise behind this is that for a given WK, there will be a sink position, a very specific orientation for a very specific range of aspect ratio class, assuming you're dealing with a rigid class and so forth. Okay? So we want to determine and find a way to clearly, if we have all the same data set, we want to find a method that will come up with the same answer for all of us. Otherwise, the method is flawed. Now, this is the very ugly diagram called the rigid grain net that you'll be using. You won't have to generate this plot. This plot is in the Excel spreadsheet that will be supplied with the lab material. And it's directly linked to a spreadsheet. So you punch in the numbers, and those class will plot directly on this diagram right here. So that component is pretty straightforward. How to read this now? Okay, so this comes from a paper by Micah Jessup, Rick Law, and Chiara Fassi. The paper and accompanied material is on OnQ, and that's all in the zip folder. The diagram itself has, on the y-axis, angled between the long axis of the class and the fabric attractor. That is the macroscopic foliation in your thin section. Okay? So 0 degree would be an object that's lying parallel to the foliation. 90 degrees would be an object that's orthogonal to the foliation in terms of long axis. So that's pretty straightforward. Okay? On this axis here, okay, we have the beta star value, which is the shape factor. Okay? And this conversion equation is right here. Mx being the long axis length and Mn the short axis. Okay? In parentheses here, these values 1, 2, 3, 4, 5, 6 is the actual conversion aspect ratio. So an aspect ratio of 1, okay, is a B star value of 0. Okay, so the square is right here. Here's the rectangle with an aspect ratio of 2 that converts to a B star value of 0.6. Aspect ratio of 6, which is the same as an immaterial line, is right here with a very high beta star, B star value. Okay? And here, what you have, 0.1, 0.2, 0.3, 0.4, 0.5, is the percent simple shear. Okay? 1 meaning 100% simple shear, 0.5, 50% simple shear, pure shear, and so forth. Okay? So on this diagram here, we have a series of lines, okay, like this. These are called semi-hyperbola. And then we have another line, that's the blue line in this diagram, which will be gray in your plots, which is called the vertex curve. We'll go through what all of these mean one by one. So let's start with the hyperbola. This line here represents the ideal distribution of grains in terms of orientation with a particular kinematic vorticity number. So if you have a kinematic vorticity number of 0.3, okay, let's go back to this, 0.3 here, this line here marks the ideal distribution of all class of all aspect ratios with a kinematic vorticity with a 30% simple shear component. Okay? So for each of these lines here, they're tying in aspect ratios and kinematic vorticity number values. So in this particular case here, this represents the range of all the class with a very high component of pure shear. The vertices, which are these two lines right here, which is essentially the break and slope, the deviation of the hyperbola from vertical to asymptotic, okay, marks the unique aspect ratio value, the break aspect ratio point, where the the kinematic vorticity number equals the critical shape factor. What you will do in the lab is you'll have a thin section and you will measure aspect ratios of clasts that obey the assumptions that are part of this method. You'll measure aspect ratios and measure their orientation, the orientation of the long axis of those clasts. In doing so, you'll get a range of clasts, which are all these blue dots, that will fall somewhere on the plot. All of these here represent grains that are freely rotating, because there's a huge range, a huge spread in orientation. These grains here, which are much more limited in orientation, meaning they're not rotating anymore. They're falling into a sink position. So you'll come up with a zone, a distribution of class, which will have a huge variation in orientation. That means that all of these class have an aspect ratio smaller than the critical aspect ratio for that given WK value. Okay? Meaning they're freely rotating. They're not stopping. All of these class that fall into these zones are class that have an aspect ratio greater than that critical aspect ratio for that given WK value for that sample. And as you can see or interpret now, the break between those two zones represent a specific hyperbola that is tied to a kinematic vorticity number. So if we take this sample here, which is an example of a thin section where 138 clasts were measured, main amphibolas and epidote clasts. On the left side are all classed with very small aspect ratios, and there's a huge distribution in orientation. And somewhere in this zone here, and this is the degree of error. If you just look at the upper part of the diagram here, all of these classes here have a sink position, very limited rotation or orientation. And the break between this coincides with this hyperbola right here. And if I were to draw it, it would be like this. And on the other side of the diagram, it would be oriented like this. That's 0.6, and that's 0.7. Okay. So here I would look at this diagram and interpret this data set to represent a series of classes that are being affected by a kinematic vorticity number somewhere between 0.6 and 0.73 WK value. That represents, if I were to convert that, 0.73 is very close to 50% pure shear versus 50% simple shear. Okay? Yep.
Where you've drawn the line seems not necessarily arbitrary, but like, do you want to catch all the points inside where you're drawing them? Because to me it looks as though it would be close to like 0.5. Like, do we ignore the outliers here, or do they all count?
So here what's important, right, as you'll see, you want to measure as many grains of as many aspect ratio differences as possible, right? So here what makes the difference here is you've got grains here, these two grains and even this grain here are clearly at a very high angle to the foliation surface, okay? As we go into this zone here, I have absolutely no grains that are above the vertex line.
Gotcha.
Okay? So this is clockwise rotation, this is counterclockwise rotation. Ideally, the clockwise and counterclockwise should match. Okay? But like any method, there's a degree of error and it depends. All you need is a couple more grains that you find here with this aspect ratio that has this orientation, and suddenly this would change. Okay. In the counterclockwise orientation, for example, I had fewer grains with aspect ratio at a very high angle. So my estimate of the counterclockwise orientation, for example, is a WK of 0.6. That's the breakpoint just because of that single grain there. Had I not measured this grain right here, I would have perhaps put the line here because of this grain right there.
Gotcha.
Okay? So of course, the more data, the better, because you have a better degree of confidence in your data set. But all it takes is one or two and suddenly your interpretation changes. So this is how to read this. You won't have to do much more than that. You'll have to measure aspect ratios of class and orient and then calculate the angle difference between the long axis of that class with the foliation. Using your microscope, that's easily done because on the rotating stage, it's calibrated. You put your thin section such that it's east-west, you put that at 0, and then you just rotate your rotating stage and look at the number when the long axis is parallel to the east-west, and you've got your degree. Plus for clockwise, negative for counterclockwise, and you'll measure these very, very quickly. Okay? Renaud?
Well, actually, you will not have to measure them in a 10 section.
We're doing it on the
because,
right.
yeah, you have full 10 section images, so you can do that on your computer. It's a bit easier than on microscope. And you also have data sets that are already, like for 10 sections where somebody already measured a bunch of grains, you will just need to plot them, interpret them.
So did Miguel, Toronto, Simon Fraser, you got that?
Yeah, we got it.
Okay. So you actually you won't do this. You'll do this on photographs, which is even easier. You just use your Douglas protractor to measure in degrees. Okay. So one of the things that I want to just finish off and make sure that it's clear for everyone is whenever you're doing this, keep in mind these assumptions and conditions. And I'll just give you a couple of examples where things can break down very, very easily. There's been quite a bit of critique out there in the literature criticizing this approach. And I'm the first one to acknowledge that indeed we have to be very careful when using it. For example, if we're dealing with a shear zone that is a somewhat low temperature shear zone, let's say 400, 425 degrees Celsius shear zone, the quartz will behave ductily. What about the feldspars? So rigid. They could be rigid, which is good, we want rigid class, but what could happen to the feldspars? They could change grain size during progressive shearing. If they change size during progressive shearing, they may change aspect ratios during shearing, which means that their rotation rate will also change, so things won't be constant during the whole progressive deformation. If you have internal deformation, so rigid porphyroclast that undergoes some ductile internal strain, if you see underloss extinction in your rigid class, for example, there's internal distortion of the crystal lattice. So the aspect ratio may change during deformation as well. Okay, so there's a lot of caveats in this, but for the sake of the exercise, the samples that we do provide you with, we will assume that these conditions are met. Okay? Let's just have a look at this thin section right here. Okay? And let's think about these assumptions for a minute. Okay? And there's the matrix here is fine-grained quartz. It's a fine-grained quartz myelinite. There's some mica grains right here. There's two large feldspar grains, porphyroclast here. What's good and what's not so good about these samples? If we're thinking about it in terms of vorticity analysis and rigid grain analysis.
Close to each other.
Speak up.
They're close to each other.
They're close to each other. So what could happen if they're too close to each other? Right? So if we think about this class here, let's say is trying to rotate this sense, and let's just say this one is trying to rotate this sense, they could counteract each other or even interfere with one another. Okay? So grains too close to each other, you should avoid measuring them because their position, finite position that you see in the thin section may be controlled by just interaction between rigid class. What else?
The grain shape.
The grain shape.
Changed.
What about it?
Well, they're not like the same. They may have changed through heat, like through the strain.
How do you see this with this section? With this image? What do you see here?
Crystallization. It's broken. Fractures.
What's around the feldspar, right? There seems to be either, a aggregate, I can't remember exactly the thin section, either there's recrystallization of that feldspar around the edges. That may not be its original shape and size. Okay? And so forth. Okay, the mica itself here, right? It's a mica fish. That has undergone internal deformation. Don't measure the micas. So there's all these different things that you'll have to think about. Okay? So one aspect of the lab will be to quantify the kinematic vorticity number of some samples. This is just a refresher very quickly. We've talked about that last week. This lab, Lab 2, also deals with crystallographic preferred orientation. Do not worry, we're not giving you a thin section and telling you to take it to a U stage and measure 600 CPO. Although that would be a cool lab, but we won't do that. Okay? We will provide you with raw data that you will import into a StairNet software package to your, and there's tons out there. If you don't know where to go, just let us know. There's some good suggestions that we can provide you with. You'll import these as text files and plot trend and plunge of all the c-axes. So you'll have the scatter plots, you'll generate contour plots, excuse me, and for which afterwards you'll interpret and draw fabric skeletons on them. And then the fun begins, the interpretation. Okay? You'll interpret based on the distribution of the c-axis, whether you're dealing in constrictional or flattening strain. If you're dealing with symmetric fabrics, you can use the Flynn diagram to position yourself in there. You could use, if they're asymmetric, interpret their shear sense, the intensity of strain, the temperature of shearing, depending on the predominance of basal A slip, prism C slip, prism A slip, ROM A slip, and so forth. Okay? So each sample will have its proper individual signature. Then you can also use the opening angle of some fabrics, those that have cross girdles in them, remembering that there's a direct empirical relationship between the opening angle of your CPOs and the temperature of deformation. Okay? And the plots are supplied as well, and the references in the lab material that's in the zip folder. The entire exercise, lab assignment, revolves around the Golem shear zone. Okay, and it's Bilbo the Hobbit, the geologist, that did part of the work, but again was somewhat incomplete in his observations and measurements. You will be supplied with a series of thin sections, and their position is right here. Okay. You will. We ask you to do a beauty contest of these samples. Some of these are for CPO analysis, and some of them are for vorticity analysis. We'll want you to essentially tell us which ones are good samples to do CPO on, and which ones are not so good. Or
yeah, actually the beauty contest samples are not on that cross-section. They're unrelated samples.
Are they?
Yeah. Because otherwise it would be way too complex.
Okay.
On that cross-section, you have either vorticity data or CPO data in an Excel spreadsheet that you need to plot and interpret it.
Okay, the beauty contest is a series. How many samples?
5.
5?
4 or 5.
Yeah,
5.
4 or 5. And those ones here, which are marked, thanks for pointing that out, Renaud. Those ones, that's what happens when you lecture the third hour consecutive. Your brain shuts down too. We're not asking you to do a full pictographic description of those samples, right? So what would make a good CPO sample, for example? If you want to do quartz CPO analysis on, what is the first thing you need? Okay, you want quartz, okay? A little bit or a lot of quartz?
A lot. Mostly.
Mostly quartz. Okay. What else do you need in this sample?
No preserved primary structures.
Okay, so you want high strain, primary features. Yeah. You want dynamic recrystallization.
Rigid grains with no evidence of internal strain.
Okay, that's for vorticity analysis. Yeah. Okay, so for CPOs, we'll have one set of criteria. Then for vorticity, they're all listed in the assumptions conditions as well. So go through those samples and go through the list and check mark which ones are better suited than others. Okay? Then you'll have another series of samples which we provide raw data, which are these ones here, some of which we supply CPO data in the form of an Excel spreadsheet or a text file. Is it a text file or an Excel?
It's a spreadsheet.
Okay, so it's an XLS file that you'll have to convert usually in a TXT file for each sample, because most StairNet software import text files. So just convert your trend and plunge in Excel, save as .txt, import that into your favorite SteraNet software, and boom, you've got a SteraNet. Okay? That's for the CPO data. Then the vorticity data, you will have a thin section. I believe this is an example of one of the thin sections.
I think it is.
Where you have a fine-grained matrix and you have lots of rigid class in it. That's one of the samples that you'll just measure aspect ratios and angle of difference between the long axis and the foliation. Okay? And then with this, you get a kinematic vorticity number from the rigid grain plot that you can then convert into percent simple shear and pure shear. Going back to the final shear zone, where are the shear zone boundaries in this? Based on CPO and vorticity. And within the shear zone, do you have a change from pure shear to simple shear, from edge to core, for example? And what is the significance of that? Okay, so that's the lab in a nutshell. You want to add anything to this?
Yeah. When you convert your vorticity number to the percentage of simple shear or pure shear, just read it on the graph. Yeah, don't try to find the equation to convert it precisely, because the error you'll get by just reading the graph is much less than the error you'll get by reading your Excel plot, because, yeah, it's from a natural sample. Maybe the grain that was 15 millimeter long was measured as 13, so it's slightly up, and you have a different vorticity number. So there's no way to try to find the exact percentage of pure shear at the third decimal with the equation. Just estimate it from the graph.
So use this plot, and then on this plot here, you could put all the samples that you used vorticity on, and put them on this plot. And then, of course, in your lab assignment, lab report, then you'll discuss the values of those, and maybe add those values to your shear zone, find a graphical way to portray your result as a true scientific report, and of course then discuss your report and your implications. Make sure you always separate your observations, your data, from your interpretation. That's the golden rule of any kind of report or scientific paper. Any other thing to add?
Yeah, one last thing. For CPO fabrics, make sure that you look at your scatter, your contours, and your fabric skeleton, and not just one of those three. Because sometimes you see something on one SteraNet, and when you look back at the raw data, it's not that convincing. And sometimes when you use certain parameters for contouring, it tweaks the SteraNet so that the fabric looks much stronger than it really is. So make sure that you present all three SteraNets, and that you look at those carefully as well.
Yeah, when you're doing contouring with SteraNet software, you can literally make it look whatever way you want it, depending on how you set the significance level and the contour interval of your SteraNet. It's a good practice to use the same significance or contour intervals for all your SteraNet, so that you're comparing the same statistical contouring from one SteraNet to the other. Okay, and having the scatter plot again clearly separated from the contour from your fabric skeleton, it goes from raw data to a little bit interpretation to a lot of interpretation when you're doing your fabric skeleton. It just segregates your thinking process in three different clear steps. Okay.
It's also a good thing to say what type of contouring you've used and what parameters as well, so people can know where it comes from, and also easier for you to make sure that you've used the same. And if you're doing another study like that in a year, then you can look back at your figure and say, okay, well, I used that, so I'm going to use that again, or do something else. But...
Okay, so this week, the second lab is quite a bit less petrography, a little bit more computer. Next week's lecture, there's only going to be, again, one lecture followed by a quiz, and you'll have the week to do that. The quiz will be on this week and next week's lecture, and you'll have time to digest it. Next week, I'm moving from microtectonics to a lot broader scale. I'm going to finish my 4 weeks with a discussion of orogenic systems. So we're going totally different scale. We're not going to be talking about thin sections next week. We're going to talk about orogenic systems, exhumation processes, and ductile fault rocks, but from a much bigger scale. And that'll be sort of a transition to the following module that will be, I think, what are we doing after? Geochronology or seismicity?
Seismicity.
Yeah, and then we're after myself, the next one online is Yajing, and that'll be on seismicity of fault zones. So that's going to be coming up, and we're going to talk about totally different things at that point. Okay? So hang in there, you're almost done with me is what I'm trying to say, okay? All right? Are we done? I think we are. Thank you very much, everyone.
Thank you.
Thanks, Lorna.